do something. So like after class, we'll talk. Fine. Okay then. So
9 rupees है
let me see. I have a few set of questions and we'll try to deal with it. But like I said, first of all, let's try to deal with derivatives, as in we must see the derivatives of a few functions in order for the integration to work, and these are supposed to go in your cheat sheet, and I hope you don't actually use your cheat sheet to cheat on the exam. So this is, if any one of you are confused or if you want to derive a formula, we'll try to do that, but we don't have a lot of time at hand, so if there is a formula that you really wish to see the derivation of, only then. Anyways, when we continue with our normal lectures, we'll also derive all of these formulas. We have this. We have sine of x, and the derivative of that is supposed to be cosine of x. Cosine of x, the derivative of that is supposed to be minus sine of x. And tan of x, the derivative of that is supposed to be secant square x. I do not remember this one. So and then we have and then the same tan. And also, apart from that, we also have the exponential. Have the natural logarithm, and what else do we have? 1 by x. Sorry, 1 by x. 1 by x as in integration of scale. You're getting what I'm saying, right? There ln x got the derivative and then e raised to x. So this, correct me if I'm wrong, I believe it is ln a times e raised to x. X, this is e raised to x again, and I don't remember any of these, so if somebody could derive it or tell me what it is. So cosec x, it's like you're differentiating 1 over sin x, so we have a minus up front, we have a sin square x in the denominator, and we have cosine x in the numerator. So this is cot x, cosec x. We have to write that successfully. So this is cotangent x, cosecant x. And then if we look at the secant of x, this is 1 over cosine of x. We have negative cosine square y. And the numerator, what do we have? As in, I can write it as cos minus 1 cos square, and then we derive and we get plus sign. Why did I write a y there? It's supposed to be x. And then it is tangent x secant x. And for cot x, we have cos x over sin x. So we have sin square x. Then we differentiate cosine x, we get and I feel like this is supposed to be cosecant square x. Actually, negative of cosecant square x. Am I right with this? So, as for the inverse trigonometric functions, I want to derive it, and but again, for what we are going to do next, that is the next 10 to 12 questions, this must be in everybody's notebook, so I can tell you how are we supposed to use it. So please note this down. This is important. And if there's anything that you are, what would you say, not sure about, you can meet me after the class. I'll derive this using the first principles, and we'll see how this comes about. So we are done here. Now we'll move on to the inverse trigonometric functions, which are a bit interesting. again erasing this. Now we'll deal with the derivative of the inverse trigonometric functions, and we'll see how we can calculate that derivative. Green and green section of those. Let's go with yellow and green. Okay then, so let us call y equals sine inverse of x. So what does this mean? Like I said, what does an inverse function actually mean? So you may have thought that these domain and range, these are trivial things, but actually they are not trivial at all. So what do I mean? I said that an inverse function can be only defined for a bijective function, because to recall, if you remember, a bijective function is nothing but just it is that something from a single set has unique pairs, in the sense that if you remember the arrow diagram that we used to draw, if this is A and this is B, I have A, B, C, D, and I have E, F, G, H, and I have unique pairs. That is, first and foremost, each element of set A is mapped, and second, that it is mapped to a unique element, such that it is injective, and it is also surjective. That is, every element here is mapped, so that we are ensuring that for every element here, we also have an element here. Because what we are trying to do is, we are trying to, if this is a function f, we are trying to produce a function g. So if you remember, for a function to be defined, the domain, that is the set from which we are taking our first element, because reiterate, all a function is just set of a's and b's. So the set from where this small a, that is the first element, comes, all the elements must be mapped to some element in this set for a function to be defined. So for that we need surjectivity in the original function, that is, for each element here there must be some link to some element here. And if you look at it, but at the same time what also happens is that we need injectivity for the original function, because it is not just sufficient that we have everything here, it also for the bijectivity to be there, what we would also need is that this function, the left, you would say the elements of the set A, the function f is also an injective function. So basically, in short, what I'm trying to say is that if I pair people uniquely, for example, if I was to talk about this class, so if I could map him to him, and let us say him to him, what I could do is I could call a different function up, and I could say I'm mapping him to him. And I would not like to go into a lot of detail of this because we have already covered it. But what I'm trying to say is that for any bijective function, you can also produce an inverse function for which you just switch the sets. So this becomes our domain, and this becomes our codomain. So if you look at it, what we are doing is, it would rather be better if I explain this to you using a graph. So let us say I have this function y equals x squared. So the point is that I have a function y equals x squared, and I am trying to figure out an inverse function. That is, if I was to call this function f of x, I am trying to discover a function f inverse that we denote using this notation, that is f raised to minus 1. That is, we are trying to deduce an inverse function. So what do we want from this function? What we rather want from this function is, as in, we switch the domain and the codomain. That is, this right here, this is supposed to be our domain because we are taking up values, and then we have corresponding values here. But then if we were to talk about the inverse function, what we want is that this becomes our domain now. For f inverse, this is our domain. So we take up values from here and we map them to values here. But if you remember, a function is defined such that for each input, only one output is produced. So, since y equals x squared is not a bijective function because it is not surjective. I mean, it is also not surjective, but it is also not injective in the sense that I can find two different x's for which I find the same value of y. So when I want to create an inverse such that y, that basically what I'm trying to say is if I was to tell it to you very mechanically, so a function is just a box. Input goes, we enter a single input, we get a single output. That is all that we need. And this should happen for all the inputs that I have. But the trouble here is that if I was to link it back to its original, if I was to turn this machine the other way around, that I enter an original output which is now my input, I must get back my original input. But the problem is, if in this function I consider y equals 4, for x I get two values. So the original function was not injective, and therefore I cannot define an inverse function. I could define if I separate out some branches, if I erase a few things, I restrict the domain, I restrict the range, and I do a few things. But the point I'm trying to make is that for an inverse function to be defined, we need the original function to be bijective. That is, we need unique pairs. For example, a bijective function is y equals x, because what is happening here is that for each input I am getting a unique output. So what is happening is when I take 2, I get 2. So when I consider any other number, let us say minus 2, I do not get 2, I rather get minus 2. So the injectivity is preserved, and also the surjectivity, that is in my range, or not, of course not range, in my codomain, that is the set to which I am mapping, I can pick up any element. If I was to think of the line, I can pick up any element and I would find a corresponding x value for which my value is achieved. So what we are trying here, if you look at it, it's just that you take an input here, you get an output here. Now in some sense we have switched the axes, as in this has now become my x-axis. This is the positive direction of the x-axis, and this has become my y-axis. As in, I have reversed the axes now. So I take up values from here and get back to the original values for the original function. So that is what we are looking at. And now similarly, we'll talk about sin x. This is the curve which represents sin x. So if I was to think of an inverse, like I said, we want the function to be injective. That is, no two values of x correspond to the same value of y. But when I extend my graph a little, I notice that for the value 1, I am indeed getting two x values. Also, for my domain rather, I need to consider the part of the codomain such that I get all my values linked to some value. So the way we define the inverse trigonometric functions is that we restrict their domains. That is, since here we do not have unique pairs in layman terms, we only consider the part of the curve such that we get unique pairs. In what sense, let us see. So what we are going to do is, since we want that each value is uniquely mapped to some value in the domain, we only consider this part of the curve. So what happens is that you get, remember that now that we have turned things, our axes have changed. So for every value of sin x, you get 1x, because all the possible values that sin x can take lies between -1 and 1. So we have considered all the x's for these values. Erasing the rest of the graph has also ensured that for each value of y, we only have a unique value of x. So because if I was to draw this curve further, for this value of y, I would also get the x. So in some sense, we are restricting our domain, and thus we define the inverse sine functions. So what does it actually mean to say sine inverse x? All it means is, for example, if I was to talk about e raised to x, the inverse of e raised to the x, if I say y equals e raised to x, we say that its inverse is rather ln x, or if I was to write it in its more explicit form, it is log x base e. What it means is, at what power should I raise my e in order to obtain an x, and that value is the value that I get from this original function. That is, I consider that these right here, these are values which I get from e raised to the x. So now what my ln x, that is natural log of x, does is that it takes these values of y and it links it to some x. And what we are basically getting is that y equals sine inverse x implies sine of y is equals to x. So here what we have here is a number per se. If I was to talk about sine inverse of 1, so what it is asking me is that what value of sine should I take, that what angles am I supposed to take such that the sine of that angle is equals to 1. So sine inverse of 1 is equals to pi by 2, because sine pi by 2 is equals to 1. I hope that is clear to everyone. That is how inverse functions behave. Like I said, you have these mappings for a bijective function. All you are doing is you are turning these mappings the other way around. So in the original function, from x, if you are getting to a particular value of y, what is happening is using f inverse x, for that particular value of y, you are getting back your original x. So if sine pi by 2 gives you 1, sine inverse 1 is supposed to give you back pi by 2. That is what we are going to deal with here. So in order to get the derivative of sine inverse x, we consider y equals sine inverse x, and then using the identity of the inverse function, we claim that sine y is equals to x, and then we differentiate both sides with respect to x. So if you remember the chain rule, so I have differentiated both sides with respect to x, and what happens is that if I was to write d of y with respect so a differentiation of y with respect to x, I could write this as dy dt times dt dx. So since my original function was a function of y, I differentiated it with respect to y, and then I differentiated y with respect to x. Now if you look at it carefully, what I need is dy dx, and this comes out to be 1. So my dy dx is equals to 1 over cosine y. And if we look at it, our y was sine inverse x. So basically we have finally achieved dy dx. But we have it in terms of y. So we need to switch it back in order in a function of x, because that is the way to differentiate. So let us see. We know that sine y is equals to x. So in order to get cosine y, what we could do is we could square both sides, and then we could do this. This is so we are getting for cosine y plus minus under root 1 minus x squared. But something special happens here in the sense that if you consider yet again sin x, we have fixed the principal domain from minus pi by 2 to pi by 2. So what is happening is that we have made sure, because like I said, you can take any set of domains such that you have the unique values and you can then define sine inverse x. But what we are trying to do here is that we have fixed a principal domain, as in if not stated otherwise, and I say sine inverse x, all of the mathematicians throughout the world agree that we are going to consider minus pi by 2 and the interval minus pi by 2 to pi by 2, because if I was to ask that which angle will give you sine inverse 1, you could give me all sorts of values, because this value gives me 1, this value also gives me 1. So they have restricted it such that whenever somebody asks you sine inverse 1, everybody in coherence can respond with pi by 2. So when we are considering minus pi by 2 to pi by 2, if you look at it, we are talking about this quadrant, the quadrant 1 and quadrant 4, and cosine of x is defined as x over r of a circle. So I consider a circle here, the x coordinate in these two quadrants, it is always positive and the radius is always positive. So I know for a fact that my cosine of if my you could say if my y is restricted from minus pi by 2 to pi by 2, my cosine y must be positive and it cannot be negative. So I put it here and I get 1 over under root 1 minus x square. So that is because dy dx is nothing but the differentiation of sine inverse x. So I get my formula. The differentiation of the sine inverse x. I reiterate the process, finding out the cosine inverse of x, and I want you people to figure out the rest. I feel exhausted, but anyways, let us amp up the class a bit. Guys, wake up. Let us start. So we have got the cosine inverse of x. So like I said, if y is equals to cosine inverse of x, y is the value of the angle whose cosine when I consider, I'll get back my value of x. So basically I get cosine of y is equals to x. And now I differentiate both sides with respect to x. So what I'm going to get is, again using the chain rule, we differentiate this, we get minus sine y. But then we should not forget differentiating it again and getting dy dx. Differentiating x with respect to x, you get 1, then you consider dy over dx. You take sine y to the other side and you get minus 1 over sine y. Yet again you can try to figure out using the identities what sine y is and what it's not. But let us try an easy way out. So I know cosine of y is equals to x. So I'll consider the triangle whose angle is y. Since its cosine is equals to x, I know if my hypotenuse I take to be y, this should be mod of x, because x is a coordinate and can be negative as well. And using the Pythagoras theorem, I can write this as 1 minus mod of x squared, but mod of x squared is x squared, because minus 2, if you take the mod you get 2, and minus 2 squared is 4 and 2 squared is 4. So either ways, because you are squaring the value regardless of what is inside, you can just write it as x squared. So now that you have written it as x squared, we are going to write what sine y should be. So sine y should be this value upon 1. But then yet again, we know that this value is just the length, because we are just using the Pythagoras theorem, we are not considering that this could be a negative value. So yet again we go back to the domain and we check the domain for cosine of x. So the graph of cosine of x looks something like this. Yet again we want to restrict our domain such that we get unique values. So I start on this side. So for these values of y, I am getting these values of x. But then I need to leave these values of y, because these values of x, because they are going to produce, if I take a look at it, they are going to produce the very same values of y. So I'm not considering this interval anymore, but I need all the possible values of cosine from 1 to -1. So I need some values from this side as well. So I consider these values again of, you could say, of x. Now the problem is, if I move further, yet again I get into the same trouble, that these values of x, if I was to extend this, these values of the x yet again produce the same y. So I'll forget this part as well. If you look at it, even the domain, as Professor Aribam says, in maths we do the most natural thing. So we went on the right hand side and we figured out that we need to neglect the left hand side. And when we moved further, we realized that we only need to take values up to here. So we have unique values for all the possible values of cosine. So cosine can take up the values from -1 to 1, and we have x's, we have angles, unique angles, such that the values are satisfied. And if you look at it, this is 0 and this is pi. So if you don't want to remember the principal domain of the functions, as in the trigonometric functions or the inverse trigonometric functions, if you don't want to remember, let us say, their range or domain, depending on whether you're talking about the real functions, the original functions, or the inverse functions, you can always draw their graph and figure out naturally how would you determine a principal domain for them. So if you look from 0 to pi, we have these two quadrants, and sine of x, or rather sine of theta, is defined to be the y coordinate upon the radius. So if I take up any y coordinate in this quadrant, that is this quadrant, the value is positive, and r, being the radius, is always positive. So I know sine theta is always supposed to be positive, so I need not introduce a negative sign here, and I can directly write it to be under root 1 minus x squared. So we get another set of formula, that is, or another formula in our original set, that is the differentiation of cosine inverse x happens to be minus 1 over square root of 1 minus x squared. So I leave you with these two formulas. You'll have to figure out the rest on your own. So what you're supposed to do is this. You are going to write y equals tan inverse x. That is going to give you tan y equals 2x. You are going to differentiate both sides with respect to x. Note that this term would come in due to the chain rule. That is, you differentiate tan y with respect to x. First of all, you're going to get a secant square y times dy dx equals 1. You send the secant square y here in the bottom. You construct a triangle. You take a look at the triangle, but always note, whenever we talk about triangles, we are talking about lengths. It is not necessary that the length, for example, in this case we had 1 minus x squared. This is simply the length. When we talk about sine theta or cosine theta or any other trigonometric function, we rather consider the coordinates in the Cartesian plane. So the coordinate may be positive or negative. So you will have to consider the domains and ranges in order to determine whether the length, when you're supposed to put back in the formula, whether it comes with a minus sign or not. And now we move to the questions. If needed, we'll also derive the other trigonometric functions. So now for the fun part, you can try to solve it with me. I'll give you about a minute or so to solve this, and if all of you are comfortable with it, we'll be fine. If not, we'll move on with the question. So I had a few questions. So all of you give it a try substituting something, and like I said, try substituting such that you can see that there's this number, and if I differentiate it, I see another number. So for the first question, I'll give you a hint, that is, if I consider this to be a variable u, when I differentiate this, I will get du dx equals 8 times x squared, the derivative of x squared, which is 2x, So I'll get 16x plus the derivative of 1, since 1 is a constant. I'll get it to be 0. So what I'll get from differentiating this function is 16x. And I see that in the question. So it is yet again very natural to take my variable u to be equal to this. Try solving it, consider u to be equal to 8x square plus 1 and see if you can work out a solution. This was your hint, and you can see u equals 8x square plus 1. I take du dx, 8 is a constant, derivative of x square is 2x, the derivative of 1 is 0, so I get du dx equals 16x. And then I take dx to the other side, loosely speaking. We don't do that in mathematics, this has some special meaning. So we can write du equals to be 16x dx. And if you input the values here, you may discover something. So did anybody reach the answer? Yes. A bit louder, everyone.
2 into root under 8 is x square plus 1.
2
Into root under
into square root
8x square plus 1.
8x square plus 1. But then, what I would like to point out is that, like I said, the integral means a function which, when differentiated, gives me the function here. So this is the correct answer. The only problem is that I can also add any constant here, because the derivative of the constant would produce 0. So whenever we have indefinite integrals, that is, we have not specified limits, that is, we have not put a number below and above this crossbar, you must always write plus c. Even if you don't write it, it is generally understood, but for the formality, we do write plus c. What we are trying to say is that if I differentiate this function, that is, I put in any constant here, since the derivative would be 0, I would get back the original function. So let us see, what did we do here? So our 16x dx was equals to du. So we write this as du. Then we have a square root, and an 8x square plus 1 is equals to u. So we have du upon under root of u, which is u of minus half du. And this is a standard formula. In the integral table you will find it, that is x raised to n. When we integrate it, we get xn plus 1 upon n plus 1, because like I said, when you differentiate this, what would happen is n plus 1 would come forward, the n plus 1 would cancel out, and you would reduce the power here by 1. So you would get x raised to the power n. Is that clear to everybody? And if I was to be more formal again, that's plus c involved.
This 8x square when we differentiate into 16x, does it come intuitively that will it come meaning that how are we doing that below the denominator that was 8x square plus 1, on differentiating it will give 16x. So is it all the time the question, or we have to think like that?
You'll have to think it is intuitive, because like I said, I gave you a hint that see that you can differentiate something and get something. So we through practice, it becomes very natural that the differentiation of x squared is given by 2x, because the 2 comes in front, the power gets reduced by 1, so you're left with 2x. So I can think that if I was to differentiate 8x squared, I would get 8 times 2x, which is 16x, and plus 1, the derivative would be 0. So I see that there is a 16x already in my question. So to me it is intuitive that I can consider this to be my u, that is, I substitute the variable, and I can figure out, we can at least try whether we get a solution or not. Like I said, in integration we have a few tricks or techniques to get you along. You can never be sure which method works, you can only try, and it is through practice that you are going to learn that whether it comes to intuition, what am I supposed to think, that is why we are going to do a lot of questions today, so that you can think about things. And there's another example which I will work for you, so that you can see how this intuition comes about. So we have 3 under root sine of v cosine of v dv. This may look like a long integral, but yet again it is simple in the sense that I can intuitively think that if I take my variable to be sine v, I see its derivative right next to it. This is not theta, this is v. So it is cosine v. So now this is the first approach that comes to my mind. It may or may not work, but at least let us try. And as you try more and more integrals, you will be able to conjure up in your mind a first few steps, and you will be able to decide very quickly that whether this is going to work or not. So let us see. We consider u to be equal to sine of v. We differentiate it with respect to v. We get cosine of v. Yet again, loosely speaking, we send v the other side, and we get cosine of v dv. So I see that I have cosine of v dv here, I have a sine v here, so the method may work. And let us see. 3 is a constant, it comes out. Under root sine v was u, so I get a u. Cos v dv was my du, so I get it here. And yet again, I can write the square root as 1/2. So I increase the power by 1, so you get u3 by 2. I take the same power in the denominator, so you get 3 times 2. And then yet again, since this is an indefinite integral, we have not specified the limits, you get a constant of integration. And the 3's cancel out, you are left with u raised to the 3 by 2 power. But remember that you specified a u, no pun intended. So the point is that since you have specified the variable u, you need to put back u in order to get the original integral in terms of v. So you put in the v and you get sine of v raised to the second power, and 2 times rather, and you have a plus constant of integration. So this is how you can intuitively conjure up. I'll do it once again for you to see, and then I want you to solve a few integrals.
While solving, if dv is removed in the solution, then we can say that the integration is done.
dv is just like a notation. When I say,
When are we able to know that now our integration is done?
let me put it this way. What is
What are the 2 steps?
yeah? What is the? It's not necessary that it happens in multiple steps. But let us see. What is its integral? Could you answer this for me? What is the integral of cosine x? Sin x. So basically, when do you know that you have solved, or rather, I keep forgetting it, plus a constant of integration. But when do you know that you have finally found the solution? Is when you can say that I have a function in terms of the original variable, that is, the original variable was x. I have a function in terms of x, that when I differentiate, I get this, the integrand. You ignore the crossbar, you ignore the dx, you need to get this function. So you can always verify your answer. The derivative of sin x is cosine x, the derivative of a constant is 0. So yes, it is true that these two match, and therefore I know I finally have my answer. Here you have your original answer in terms of u. But the question never specified what u was. You rather believed that u was equals to sine v. So you need to give me back the original function, so that when I differentiate this original function, I get back my original function. And let us try doing that as well. So the constant of integration, its derivative is going to be 0. 2 is a constant, comes out. 3 by 2 comes out. And we have sine v under root, and the differentiation of sine v is cos v. So if you look in your notebooks, the 2 and 2 cancel out. If I'm not wrong, this was supposed to be your original integral or integral, right? So that is how you can always verify whether you have got the right answer or not. Our purpose is to produce a function in terms of the original variable, such that when that function is differentiated, I get my integral. That is all you need to do in order to get the answer. And let us get to our next integral, that is 16x dx. this is a definite integral. We have our limits, so we won't be needing the constant of integration. We have 16x dx upon 8x square plus 2. So yet again, very intuitively I can think that 8x square when I differentiate I get 16x dx. So it is very sensible to consider this entire term as my u, because anyways the derivative of 2 is going to be 0. So I substitute u equals 8x squared plus 2. I differentiate both sides of with respect to dx. So I get 16x plus 0, and rather than writing another step, I am directly sending my dx here. So I can directly replace my du with 16x dx. I put it back here and I get 16x dx happens to be du and 8x squared plus 2 happens to be u. We know that its integral is going to be ln u plus c, and no, rather not c because it is a definite integral. We are going to keep the original values. U actually was 8x squared plus 2. So in definite integrals, after you have finally found your function, what you are going to do is you are going to evaluate the upper limit and you are going to evaluate the lower limit, and you are going to subtract the lower limit from the upper limit. For example, in this case, we have 1 here, we have 0 here. So we keep 1 in the function and we get ln 10 minus, we keep 0 in the function and we get ln 2. And ln m minus n is ln m over n. So your final answer comes out as ln 5.
Why put a mod here?
Mod. I'll tell you why we put a mod here. So if I draw 1 over x, the point is that 1 over x is defined in its entire domain except at the point x equals 0. But when I consider the graph of ln x is only defined in its positive domain. But at the same time, in 1 over x, I can even have negative values. So what I am trying to do is that let us consider the function ln of mod x and then try to differentiate it. So ln of mod x when differentiated yields 1 over mod x. I am taking this using the chain rule. I am taking this function and then I am going to differentiate mod x itself, and then we consider cases. Am I doing that right? This is ln of u is 1 over u times, I then differentiate this function, and if my mod x, let us say my x is greater than equal to 0, my mod x equals x, and dx over dx, or rather I should say differentiating x with respect to x, yields 1. So I get 1 over mod x. And since x is positive, I can say in this case I directly get 1 over x. But since x is positive, I would say that it is the same as 1 over mod x. Now let us consider the negative of that. So what we are going to get is we have 1 over mod x, and this comes out to be the negative of x, that is, let us consider if it's negative, we have this, the minus sign comes forward and we get minus 1 technically from here, and this would open us the minus sign and we get 1 over x again. So the point I'm trying to make is, if you take the ln mod of x, you always get 1 over x, regardless of what your x is, because since I've considered the mod of x can now be positive or negative. To reiterate, even here since x is positive, I still get 1 over x. So regardless when I considered x greater than equal to 0, no, it cannot be equal to 0 because we have 1 over x, the denominator becomes 0. So regardless whether I consider x to be positive or to be negative, when I consider ln x, that is, like I said, if I differentiate ln x, it should rather be d over dx here, I've written ln x. But when I differentiate ln x, I get this function. So when I integrate this, I should get back this function. And the reason I have put up a mod here is so that it works for the entire domain of 1 over x, because now we are talking about 1 over x as a function. So in our mind we are thinking that fine, we need to go back to the original function. But in order, when I say 1 over x, I mean all values of 1 over x. So for that, I need ln of mod x rather than just ln x. Though this is a very subtle thing usually people miss, and I believe if you miss it in the exam, I don't think you're gonna get negative for it, but just to be on the safe side, because you might get a negative for it, because I remember there was this paper, if you remember the circular motion question that we went over, there were a few people, if you remember the answer was something like L naught E of negative of lambda t upon m, something along those lines. But when we originally had the quiz, a few people missed out the negative sign due to confusion in the sign convention, and they were given 0 marks for it, because Professor Sheet was a bit rigorous about it, because he thought that it's a long story, but the point is, even for a small negative sign, even for a small subtlety, you might lose all your marks. So it is better to keep such subtleties in your mind when dealing with things. And now I have showed you 3 integrals, so you might be getting an idea of how to deal with integration by substitution. So let us deal with the next question, and let us see whether you can figure this one out or not. So I'll give you a minute or a couple of minutes to solve this, and let us see who's the first one to solve it. As soon as you solve it, you may feel proud enough to shout the answer. Forgive me if I am not a little more entertaining or engaging today. The point is that I find this practice is a bit boring, because we haven't even discussed what integration is, and yet we are trying to integrate functions. So, these are not things which are very exciting, but nonetheless these are the most useful things, because at least while answering your paper, you need this. You need not know what exactly a derivative means, what exactly an integral means, as you would have seen in an assignment question. It does not matter whether you understand your integrals or not. As long as you can find expressions, or as long as you can calculate expressions like this, you are safe and you won't have any trouble scoring points. To reinforce, if you remember that the derivative of a raised to the x, where a is a constant and x is a variable, happens to be ln a times a raised to the x. So you may need to use that here. Has anybody got the answer yet? So we needed these sessions. This time I was thinking this may be too easy for you. I believe it is too easy for you people. You are just a bit merciful on me. You don't want to break my confidence. I'll take that. Did everybody get the answer? Okay, then all eyes on the board. So what we are trying to do is, like I said, we are trying to break down.
Yes, 3 into ln x. 3 into ln 3. 3 into the power x.
So basically, you're saying 3x plus 1, right? 3 raised to x plus 1. And take a constant of c. It's fine whether it's not fine if you miss it, but yeah, that is for Professor Sheet to decide whether it's fine you miss it or not. But yeah, I'll let you lose on that. So we have a candidate, and let us see whether he's right or not. So like I said, what exactly are we trying to do? We are trying to break down the original integral in terms of something that we know, as in we are trying to get it something of this form. We do not want x plus 1 over here, we don't know that, but we know if we could get something like 3u, I know how you could get back 3u, because if I differentiate 3u, and this is d of du going here, that is I am differentiating this function, I would get ln 3 times 3 of u, but then ln 3 is a constant. So if I divide this side by ln 3, I know that my constant would come out on differentiation. and I would get 3u. So I know that if my function looks like 3 raised to u, I can give this as my original function. So when I differentiate, I get the original 3 raised to the u. Or rather, when I integrate this function, when I differentiate this function, I get 3 raised to the u. So when I integrate 3 raised to the u, I get 3 raised to the u over ln 3. Did everybody get that? What I did there? Any confusions? You want me to go over it again? Yes?
Repeat that one.
Okay, so what I'm saying is that I claim d over dx of 3 raised to the x is ln 3 times 3 raised to the x. Does everybody get that? Aloud yes, please.
Yes.
Oh, we get that. But what I'm trying to do is, this is just a side practice. What I want is that I want an expression on differentiating which I get 3 raised to the power x. But here I get 3 raised to the power x, but this constant ln 3 is bugging me. But I remember that if I put a constant here, that constant may come out here as well. So what I'm going to do is, I'm going to change my original expression, and rather than 3 raised to the x, I'll divide that by a constant. Natural log of 3 is a constant. All it means is that a number, when I raise e to that number, I get 3. So that happens to be a constant number, right? So when I do this, the only change that would happen here is that initially I did not have this constant. So this constant would come out as it is. So ln 3 comes out as it is, and the ln 3's cancel. So now I finally have a function differentiating which I get 3 raised to the x. So my original question, which function do I get when I integrate this? So I have that function here. But the point is, we know that for 3 raised to the x, we do not know that for 3 raised to the x plus 1. So what now?
You will separate it.
We could separate it,
3
but
into 3 to the power x.
yeah, you could separate it that way.
Yeah, that is the
Yeah. So you so our candidate turns out to be wrong, but at least he gave me an answer. I'm really happy for that. So we could use the exponents thing, or we could do another thing as well, which is the long way, that is the substitution thing. The only reason why I'm so much enforcing substitution and why I started with it is because you had a problem in your assignment which was related to substitution. So I hope that if you are comfortable in dealing with substitution, you will be comfortable dealing with questions in your examination. So let us say I consider x plus 1 to be u. So I get du over dx is simply equal to 1, because the differentiation of x is 1 and 1 is 0. And I send the dx to the other side. So I guess du is equals to dx. I substitute that here. So 3 raised to x plus 1 is u and dx is du. So I have the original form. So how did I know I must put u equals to x plus 1? Because I knew I could solve something of this sort, and I looked that when I differentiate this, I'm going to get 1, and when I'm differentiating it, I'm going to get 1. Dx is going to the other side. So this is going to become du and this is going to become 3 raised to the u. Another way to do this, like your friend suggested, this is 3x times 3. 3 being the constant happily works out, and here we know its derivative, and then you can solve it. But you could also solve it this way. We know the derivative is going to be 3u over ln 3 plus the constant of integration. U happens to be x plus 1. We are going to get the same thing here. 3x dx is going to be, like I said, simply 3x over ln 3. The 3 multiplies and it gives you the same answer in both places with the constant of integration. So you can go either ways. The point I'm trying to make is that I'm enforcing substitution so that, like I said, you can also have some intuitive idea, though intuition will only take you so far. And let us look at another question, which is a bit more tricky on the appearance. But like I said, if you're comfortable enough with differentiation, if you have differentiated enough number of times, which I believe you would have for your competitive exams, like I said, carefully look at the integrand and think that when I differentiate something, can I get something else? As in, you'll have to think that. So this is actually a very nice question. So we have the integral dx under root x times under root x plus 1. So you'll have to be a little careful, and if you're careful enough, you will be able to see that differentiating something, you are able to obtain something else. So try to do that. And this actually uses the most elementary differentiation formula for the hint, the one that I started with. So it looks one of the toughest one, but it is the easiest one. Whenever you think of differentiation, there is this first very simple formula that you consider or remember, that is the differentiation of x raised to the n is n times x raised to the n minus 1. That is all that you need to use here, and you will be done. So it may look hard on the surface, but it actually is very easy. Whereas in integration, you'll see that a lot of times there are things which look very easy, such as the integral of secant x. It is a very small function, the secant, but it is going to take a little effort for us to figure that out. Yeah.
2 times ln 2x plus
2 times ln.
2x plus 1.
We have a candidate here, and let us see whether the answer is correct or not. So, like I said, I know if I differentiate, 1 is going to just be 0. But I know when I'm going to differentiate under root x, there is something special that happens. This may not ring a bell, but if I write it as this definitely will ring a bell. The half comes in front, and we have x minus half. And when we have x minus half, it is this. So what basically happened was this. If I was to iterate again, because when I take this as my u and I differentiate, I am getting a constant times under root x in the denominator. When I consider this entire integrand, I see that it is 1 over under root of x in the denominator.
Root x plus 1. Root x is root x
Root x plus 1 भैया और the whole
root x
Well,
only the root x
plus 1.
only the root x becomes
Only
over
root
x
x.
one
Okay, so there is no 1 here. This is what you are saying.
plus
Root x plus
plus one will be
outside
So what he is saying that
Plus 1 is outside.
yeah
this is the answer.
no root is the
Oh,
only
okay,
the
okay.
x.
This is the answer.
Yeah.
Okay, fine. So, what we are going to do now, like I said, I see that if I take this as my u, this has no value when I differentiate. And this gives me a 1 over something, root x in the denominator. And I see that is exactly what I require here. So, using the most, not fundamental, but I would say elementary formula, that is d of this, d dx of this. What I'm going to do is I'm going to assume that u is root x plus 1. I'm going to differentiate with respect to x. This is 0 and this comes out to be 1 over 2 root x. Can everybody work that out? This is x to the power half. The half comes in front. I have x raised to minus half, which is half minus 1. And x raised to minus half is in the denominator. I get a square root of x. And I send the dx on the other side as always. But I see this in my question. So what I'm rather going to do is, I'm going to take the 2 this side. And I have this in my question, as you can see, that is this part. So I can write this integral as 1 over under root x dx. I can write as 2 du. This is done. We are left with this. And this we took to be our u. So we have this. The 2 being a constant steps outside. And this 1 over u du, we just saw it right now. This is nothing but 2 ln u plus the constant of integration. We put in the original u, and the original u was under root x plus 1. So yet again, very close, but we did miss a mod here. So yeah, that's nice that you were able to figure this out. Remember that 1 over u du, or rather 1 over u, when you integrate, you are going to get ln mod of u, because like I said, when you are considering only the function of ln u and you are differentiating, it's fine if you are getting 1 over u, because it is understood when I write ln u is a positive number by nature, because log can only take positive numbers as its argument. But when I write 1 over u, it is not explicit that u is positive. So we must always consider both the cases where u is positive as well as negative. So this produces as its integral. Here we are integrating, here we are differentiating. So that is a small subtlety there, but very close to the answer. I like it. Let us see what lies ahead. Okay. So we are done here. Any new questions? I told you the differentiation of tan x, right? You have that written. Okay, then this will be child's play for you. Very easy. Like I said, you look at something and you see whether I can get something else or not by derivating or differentiating. And you have 30 seconds for this question. This is an easy one. So like I said, in integration sometimes the expression looks massive and dangerous, but it's very easy. But then there are expressions which we'll deal with, which will look very easy on the surface, but you'll have to write a couple of lines to get there. Like I said, there must lie something in the function, you differentiate it, you get something else, and then you may try, and you may fail or you may succeed. But since I've already mentioned that these questions are to be solved using substitution, so you have the hint that yes, they can be solved through substitution. You just need to figure out the right substitution. So 10 and 9 and 8 and 7 and times up. So
e to the power
sorry, e to the power
n
tan b
plus
plus c. Okay, I like that. There's a plus c involved as well. So let us see. I know that the derivative of tan b is secant square b. So it comes to me very naturally that it would be useful to consider u to be equal to tan b, and I have du dv, and tan b gives me secant square b. I take the dv the other side, loosely speaking, and I get this. So I have this in the function in terms of u, and so this. So I get e raised to the power u because tan b is u, and secant square b dv I can write as du. And this is very simple, that e to the u is the function which does not change on differentiating. So you get e to the u plus c, you put back u, and you get e raised to the tangent of v plus the constant of integration. So that yet again is a simple problem. We are done here as well. Let us move on to the next question. I hope you people are enjoying yourself. And let us see which question we take next. Okay. And we have this. We have this and this. Excuse me, let us try this question. Yet again similar to the last question, and let us see whether you can solve this or not. You have 5 minutes, and this one I'm going to wait a little longer because I want each one of you to be able to solve it. Yet again, like I said, there's a square root in the denominator, and you know when you get a square root in the denominator, we discussed it earlier, and I believe that you can even see that variable in somewhere in the integrand, and then you can figure out which variable to take in order for your substitution to work. These questions are similar to the last ones. These are similar questions. Next up, we take this. See. And in the meantime, let me write. As soon as you are done, you are supposed to say yes, I'm done. So I just need to hear that you are done. I just need, because I need that from everyone. So once you are done, you just need to say I'm done. That's all. Straight up by here, let us say I want to consider y is tan inverse x, and that makes tan y equals to Is everybody done? Everybody, I need a yes. Are you done, sir? Sir, behind you, are you done? Were you able to solve this? You're not able to solve it. It's completely fine if you're not able to solve it. Even integration is something that I still suffer with, and that's completely fine. So, are you done? Is everybody else done? Supriya, are you done? You're not done. It's fine. It's completely fine. It might amuse you, but I did not study the entire calculus in my intermediate. That is, in my standard 11th and 12th, I never read or studied any calculus. So whatever I have learned in college here. So if that might give you a little bit of relief. So let us see. Like I said, we have d, b, whatever u, and when I consider under root u, I get 1 over 2 under root u. And I see that here. So I can see when I consider this to be my, what would you say rather? This to be my function u. In some sense, the 1 over 2 under root w here I get for free. So though I'll call u as my under root w, I get du over dw, I get 1 over 2 under root w, dw goes there. And from here I get 2 raised to under root w is 2 raised to the power u, dw is dw to this is du, and we have the integral. So we have taken care of this and we have taken care of this. And like I said, would somebody remind me what does this add up to? If I'm not wrong, this should be this, right? Because when I differentiate this, I get ln 2 raised to the power u, the elements cancel out, and I get the original 2 raised to the u. And then I assumed u to be something which was under root w, and I get an under root w here. In the denominator, I have ln 2 plus the constant of integration again. So it is completely fine. I did not want to do this question, but I want you to remember this. So I'll do this question again. That is, now I want all of you to solve this. And as quickly as you can. Especially the people who were not able to solve it the last time. Now I believe it is very obvious. You have an under root in the denominator, you see under root elsewhere, and you can figure out a way to choose the appropriate variable for substituting. And we shall consider which question to take up next. We are done here, this one's easy. So I believe this is going to be an interesting one. So, did everybody solve this question? Sorry?
Yes.
People who could not solve it the last time, are you able to solve it? It's completely fine if you're not able to solve it. It's completely fine. Like I said, an under root t in the denominator, and under root t in the numerator. So I know when I differentiate under root t, I'm going to get a 1 over 2 under root t. I can use that to my advantage. So I say u is equals to under t, d over dt is going to be 1 over 2 under root t. I send the dt here, I take the 2 from here to here, and now I have this part of the equation, which is this, and I have this part as well. So this is nothing but e raised to the u, and this entire thing I can write as 2 of the u. 2 goes out, I get a du, 2 is constant, I get e raised to the u plus c, and u is, what was u again? It was under root t. Did everybody get the same answer? The people who were able to solve, the people who were not able to solve. The way to go about mathematics is sometimes you're not able to conjure up answers or approaches in your mind. You try your best, When you look at the solution, you do not look at the solution trying to remember the solution, or if I get a question like this, I would be able to solve this. Rather, you build your mindset thinking, asking yourself the question, what was it which I could not think? What exactly was it that I was not able to think? Were you not able to come out here? Were you not able to differentiate this? Once you differentiated this, could you not think of getting the 2 here so that you can obtain this expression right here? What exactly was it that you missed? So the point is, because you are never going to see the same question again, even the textbook reference that I am using to give you question. For substitution, it has 36 questions, and there are ample amounts of textbooks in the market. So you cannot work your way through maths like this, that okay, this particular question is solved in this manner, so I remember this. Rather, what you need to do is, you need to consider in your mind that, fine, this is something that I was not able to think. It's almost like collecting a toolkit. Like I said, most of you are smart, but I am not. So I rely on the older mathematicians. So what I do is that they have given me tools. Whenever I come across a concept, there are things which I cannot come up with. There are things that I cannot think on my own. So I see what was it that I could not think of, but they did. And I take that in my toolkit. So the next time when I'm dealing with my problem, I can think, okay, fine, there is this way to think about the problem as well. So that is how you're going to deal with mathematics. And at least I prefer that way. But I believe most of you are smarter than me, so you may choose the way you see fit. And for a change of pace, I would like to change the chalk color. Yellow is getting boring now. What pink chalk? Is it visible on the board? Is it visible to everyone? Okay, then we'll work with something else. We've got more interesting colors. I believe is it visible in the camera? No, then it works. I'm terrible at art, so please don't judge me. And I'm terrible at most of the things. I'm just not so terrible at a few things. Let us see. So coming to the next interesting question. You will have to push a little harder, but it's completely fine if you cannot think of the solution, because it may take a while. It's completely fine. Give it a try. There's no need to worry whether you can or cannot solve it, because eventually you will be able to. Is anybody able to solve this yet? And just for the, are you able to solve it? What's the solution to this? 1 by 2u whole into ln
1 plus 9 u square
1 plus 9
u square
u squared
plus c.
plus c. And we have it like this. Okay. So we have a candidate, and let us see. So the thing what happened here was, you see a 9 here, and the first intuition that comes to mind is to take a variable to be 9u squared. And we do that. And then we derivate or differentiate, and you get an 18u, and you are still left with a du. So even if it was 18 du, you could still send the 2 to that side and get 9 du. But you cannot get rid of this u. But if you think carefully, what happens is, when you differentiate x raised to n, the power decreases by 1. So if I was to get rid of u here, it is sensible to take something of u sorts here. That is, I do not want to take something of the second power, I rather want to take something of the first power. But then the question is, what should my constant be? Since I am taking L to be something times u, ku per se, and we'll decide what k is later, I can think in my mind that L square is going to be k square u square. And then I think that it would be useful if I can make my k square into 9, because I'll be directly be able to substitute my L over here, L squared over here. So I want my k squared to be 9. So it is sensible to take k to be 3, so that here my L square happens to be 9u squared. And when I differentiate it, my other purpose is served as well, because 3 is a constant, u, the derivative of u with respect to u is 1. I send du to the other side, and I get 3 times du. And since I want 9 du, I multiply 3 on both sides, and I get 3 dl equals to 9 du when I consider L to be equals to 3u. And now put it back here. So I have 1 plus 9u squared. 9u squared is L squared, and then I have 9 du. What is 9 du? 9 du is 3 dl. 3 is constant, it walks out, and we are left with this. And this is the reason why I already told you that d of dx of tan inverse x, if I am not wrong, happens to be 1 plus 1 over x squared. I did not tell you yet, I derived it, but I am telling it to you now, that is. And how does it come about? I'll show it to you quickly. Again, y equals to tan inverse x, which tells me tan y is equals to x. I'm going to differentiate both sides with respect to x, and I get dy over dx equals to 1. Can everybody get it to this point? Y equals tan inverse x. So tan y equals x. I differentiate both sides with respect to x. Dx equals 1. When I differentiate this, first I differentiate with respect to y. I get secant square y, and I'm left with multiplied by dy dx. Did everybody get it that until this point? I'm using the chain rule here. And my dy dx comes out to be 1 over secant square y. And I'll give you another important identity which says 1 plus tan squared theta equals sec squared theta. And to verify it, like I said, it's very easy. You take 1 plus tan theta, you get y coordinate upon x coordinate by definition. So you get y squared over x squared. And then sec squared theta is 1 over cos squared theta. And cos squared theta is x squared upon r squared. The x coordinate, r is the radius. And then I consider x squared plus y squared over x squared equals to r squared plus x squared. But x squared plus y squared is just r squared, because under root x squared plus y squared is equals to r. So these get cancelled out and these get cancelled out. What I'm trying to show is that the identity holds. So this is a true identity. So I'm going to use that here. This got a bit dirty, but anyway, dy dx 1 over secant square y. So I know tan y equals to x. So I can say tan square y equals to x square. I can add 1 to both sides. I guess this. I know 1 plus tan squared y secant squared y. And you are left with 1 plus x squared. And then we have 1 over secant square y, and secant square y is 1 over 1 plus x squared. And dy by dx comes out to be 1 over 1 plus x squared. And we know y was a tan inverse x. So what we can say is d dx of tan inverse x is equals to 1 over 1 plus x squared. This is an important identity which you shall remember or derive if you feel like it. The people who have trouble remembering all these identities, you could always make up a triangle if this is y and tan y is equals to x. So let me consider that, what do I consider? Let us consider this length to be mod x, mod k, rather if I consider this length to be mod k and this to be mod k, I always get tan y equals to x. If I was to think about the hypotenuse, I would get x squared plus 1 and the mod k comes out. If I was to think about cos y, the k's would cancel out and I would get 1 over under root x squared plus 1. And when I take the square, I get 1 over 1 plus x squared. This made the triangle method. I will like go more in depth. I went over it in a hurry. So let us say I have a triangle here. This is my angle y. And I know that my tan y is x. So I can think of this to be x and this to be 1. But when I say this to be 1, in some sense I am meaning its length to be 1. Because the x coordinate can be positive or negative. And when I say this, I mean mod of x, because yet again it is just the length. So what I get for this is 1 plus mod x squared, which is the same as x squared, because minus 2 squared and 2 squared are the same thing. So I get it here through Pythagoras theorem. And what I need is 1 over cos y. So when I consider cos y, I get mod x over 1 plus x squared. And this is just the ratio, because I don't know whether this is positive or not. So I do not know whether there is going to be a plus or minus sign here, but there's a trick up my sleeve, because I do not need the secant y, I need the secant squared y. Did I do this right? Let me think again. No, there should be a 1 here, sorry. So there's a 1 at the bottom and there's under root 1 plus x squared. Fine? So like I said, these are just lengths. This my x coordinate, which I assume to be 1, it could be minus 1 as well. I'm just talking that its length is 1. But I consider a plus minus because this is supposed to be always be positive because this is the radius. So I know this to be positive, but this can be plus or minus. But the beauty of the problem is I do not need secant y, I need secant squared y. So the plus minus is irrelevant because plus x squared is the same as minus x squared. And I get, when I square them, what I rather get is, I believe I've yet again made a mistake, because I have to take 1 over, no, this is fine. So we have secant square y as 1 plus x squared. So 1 plus secant squared y is the same as 1 plus 1 over x squared. I hope that is clear to everyone. Fine? Works? So using the triangle method, you can get this as well. But generally when you use triangles, the problem is that you need to be well aware that you are talking about lengths, because we are assuming this triangle could very well, this y angle could very well be this big to produce a negative x coordinate. So for that you need to be mindful. You can go through your identities. When you go through identities, you have to be aware of the domains and ranges. When you go through the triangle, you have to be aware of the domains and the ranges and the fact that you are using lengths. So when you actually write the ratios, you must be very mindful about the fact that the x or the y coordinate can either be positive or negative. So I believe once we accept this fact, this integral becomes easy because it says 1 over 1 plus L square.